So you go through a Z transformation, right? And then it goes in with the normal, right? Normality is 0, 1, right? So the variance is 1. So you have to convert this now, right? You don't need to convert because the package does that for you. So it puts it into this standard normal. If you use the set, then the standard deviation is actually 1. Okay, so it's just like this is 1, right? And then this is another 1, right? So it's 2 and 3. So this is what we are saying. This is not related to this, right? Because this one is the value, right? Let's say this whole value which adds up to a standard deviation of 2.8, for example. It's not related. It's just part of the requirement by Z test. Let's say Z test you run, if some package they will ask you to provide, okay, what's the value here, so they can reference this value before they calculate. Some package doesn't require, right, because they can still calculate for you in the package, right? They can calculate this out and then they do a formula. Because yeah, not related. It's just a requirement by the test. And I think what y'all get is correct. In a way, you mentioned until the non-parametric and parametric, right? Yeah. So for parametric, the requirements is quite straightforward. Is normality, that's number 1, right? And then okay, the homogeneity of variance, but if you got a t-test, if they have variance unequal, you can choose, right? But then outliers, right? So the main concern is actually this guy, the normality, right? Because this one is the one that actually affects the other 2, right? I mean, if it's good, right, most likely this 2 is also more or less good. And this one you mentioned correctly, you can do a test like Shapiro, which is for smaller data set, right? But it is okay to use it for larger, just that the results may be less accurate. And then Agostino, right? Okay, so this one is for larger data set, like if you thousands, you can use this. This one is like less than thousands, right? You can use this. Of course, there are other normality tests that you can use. So you say histogram. Histogram can also does that, right? With let's say KD, because histogram and KD can suggest, right? Because this is one way, this is another way, right? But this one visual way is not so accurate. This one also, number 2 is also sometimes it may not be accurate. So we cannot, that means we cannot use one method. Sometimes they are not very accurate. Sometimes. So if you want to use normality, you have to use more than one to affirm the decision. And the requirements, of course, is quite varied. Like this one is less than certain samples, right? This one is a large test, but the accuracy will drop. But it is usually used for very large data set. So it's also called your normal test, right? So each of them has their pros and cons, right? But we used it to collective together, because if you just basing on this one, maybe you missed out. Actually, there's an outlier. You get what I'm trying to say here, right? Then QQ plot also can check. Number 3, right? QQ plot also can check. Is from this case, it's not only for outliers. This one is for normality and then randomness as well. So they can check. So in a nutshell, 1, 2, 3 works together. But if you just use one, it's okay. But it's prone to issue of you having a quick judgment on this is normal. And this one works much more effective if you put in the theorem CLT, because you start to observe, right? N equals to 10 versus N equals to 100, and then maybe N equals to 1000, right? The central limit theorem, it suggests that it actually by right is 30 only, but you will see that CLT theorem is like this, based on histogram. You can also put KDE in. Based on that, they will converge to normal based on CLT. And using this, you can kind of explain what you say. Oh, you know, okay. So this part, understand, right? Just now you were here. So that means there are many ways of checking normality. You can just use one way. Right? And it is a requirement. But some texts say don't need, but it is a requirement because the test requires that. It's not that we want it. But your data set, for this part, are you clear? This portion? Okay. Yeah. Yes, you can use another one. Yeah, correct. Okay. But there is a problem.
Sorry,
Yes, correct. What question?
Sorry, Johnson. I'm actually totally confused on this. I feel my understanding is for the distribution, that the data that we have, right? So when we need to do a t-test, c-test is basically have to do the conversion of the distribution. What is the mean converted to become 0, so that your standard deviation for the C is, because it's 0, 1, 2, 3, right? That is, each one is one standard deviation, and then minus 1, minus 2, minus 3.
Correct.
So you convert that distribution to the C and compare whether this is actually, what is the possibility of this is fall into the standard distribution that is from the conversion from the C test.
For if you are talking about Z-test, yes, Z-test is Z-test. T-test is also T-test. They are separate tests, but both of them are similar, because T is actually, we saw it, right? T is actually a small subset of Z. The distribution looks smaller, so the T will also tend to Z. But it's just that T-test doesn't require you to know the population information or parameter.
Okay, so for us, if we have distribution, we want to check whether the possibility of this distribution is out of these 3 standard deviation, whether that is what is the possibility of these 2 sides, right? In the 2 tails, is that correct?
Very close, because you see the tree distribution is 99%, but if yours is 95%, is around 2.58 standard deviation, around there, right? So very close. So what you mean is correct, but you are looking at the tails versus the within that standard deviation. You are right. The understanding is correct, but the confidence interval, it depends on what you set. So if you set confidence 99%, right? Because you said 3, right? 3 is 99%. So that means your alpha you have to set to about 1%, because this is 3SD, right? 3SD is about 99%. So which is your CI also, right? CI, confidence interval, is equals to 99%. So your alpha, you are just looking at the 1%, which is 0.5% each. Yeah. So so the understanding is similar. Yeah, what you mentioned, the understanding is similar. So
our test for the C test or T test is basically to check whether they fall within the normal in the center this three standard deviation or fall out of the tail that beyond this three standard deviation plus minus three standard deviation. Is that correct?
Correct. So what we're doing is just like this. Yeah, correct.
Okay.
But it's probably 95% now. I mean, if you don't talk about 3SD, so it's about 2.5 something. Like, yeah. So it's correct.
So in a sense, for if there's a hypothesis, right? So you have H equal to the test and H naught, right? And if that is beyond the tail, it become H naught. Is that correct?
Yeah. If it's beyond the tail, yes, HA or H1. That means there's a difference. For example, there's a difference. So either tail, it can be this tail or this tail, right? Both are the same.
So the tail is one is positive, one is negative. That's all right.
Yes, that's all. Like positive, negative. There's nothing much different because it starts with 0 because the mu is 0. Remember the parameter of being normal, right? Is 0, 1. So this one is variance, and variance is equals to 1. If you square root, the SD is also equals to 1, which is the same as the SD here.
So for log, what normally we do is for look at the distribution, that is a normal distribution. Then we from the normal distribution, because your mean may be could be a 10, right? Then you will the system will automatically convert it to let's say for example doing C test, you convert that to the mean will become 0. And then plus 1 standard deviation, plus 2, plus 3, and minus 1, minus 2, minus 3. Right?
Correct. So they will convert into standard normal.
Yeah, but this part we don't need to do, right?
The package does it for you. The package does it for you. If you see actually, you can reference mathematics book. They will show you how you calculate. But a lot of software don't require you to do this because this one there's a lot of work in this that they convert into this. So one intuition is the standardization of score, but that one is only for calculating the critical region. Remember the Z equals to X minus mu, right? So this one is for us to calculate only the critical region. When you have a raw data, right? Let's say for example, then you can actually calculate this, right? So this formula, right? If you all remember, so this is something similar in the package as well, right? So they will have something like this, but it's just that they do it for all of the values here, all of the values, right? All these values.
Yeah. Okay, thanks. I think just clear some of my head.
No worries.
Thinking correct. So on this, sorry about that. Yeah.
No worries. Feel free. Any other questions on this part? All right. Yeah. Okay. So I want to mention also one thing, because real world data set is not so straightforward. It's not like we can convert. We can straight away use it. Like we run normality, right? And then because of assessment purposes, we still need to do that, right? So what you require for your group, right? For your group, I mean for individual, you can make assumptions even if it's not normal. But for your group project, so if you don't meet these 3 criteria, right? Let's say you don't meet these 3 normality, but you still need to run this, right? Okay. So what happens, right? Is there is a few ways. Number 1 is you can do a stratified sampling. Okay, number 1, but it doesn't guarantee. So it must before that it doesn't guarantee, but it's close. Number 2, the reason why stratified is because they have balance, right? Some of this, but okay, maybe there are some common classes, like we do some stratified. There are some common classes like this, right? So the rest are about the same representation. If you do random sampling, you will get a uniform. So we don't want uniform, right? Like this. We just want something that is like this. But it doesn't guarantee, as you can see here, it doesn't guarantee. So the number two, right? Number two is if you don't use stratified, right? What can I use? Okay. Is transformation correct? Is part of the transformation is scalar. You transform the data, right, into something that can fit into the bell curve, and this is what has been used in machine learning, right, as well. So you can use min max, you can use others, but for statistics, we want to use a transformation that retains the shape. Okay, because there are a lot of transformation like non-linear, right? Box plot. Actually, by right, non-linear may change your bell shape into something else. Okay, this doesn't violate the test, but it violates the data set nature, right? So if you are using it as a test to interpret the result, your shape is different, you are interpreting a different shape. So like, let's say I use box plots, right? Example, rather than I use min max, because min max retain the shape, right? So box plot changes, my shape is, by right is like this, right? They change it to something else, maybe like this. And then I'm using this to do a t-test. Imagine, I just take a sample, whichever, right? Let's say part of it. And then what happens is I'm interpreting based on this result. Can you see that? It's not the original result. Okay. But if you use min max, right, you have the same shape back, but it's the scale is being scaled smaller only. Like is yeah, it can be min max, it can be any other, but as long as they retain the same shape, right? That means you did not change the distribution. But this non-linear one could have changed your distribution to something, and the results are interpreting something else. You want to interpret the original one, but it's just that reason you use min max just to fit into the normality. So that means you have to rerun again to check normality. So this part, this portion, is it clear? Number two on the transformation. Okay, but there is also one problem because it's a real world data set. So you interpret, right? You cannot use this to explain as in a business context. Because how are you going to say this is a, let's say a log transform value of 2, right, to the business? Let's say it's a log transformation or min max. Very hard, right? Very hard. Because you tell the business, this is a log transform. They don't understand. So this part is not in stats, but it is in part of business where you need to explain. So what do? You untransform them back, or de-transform back, right? De-transform them back. So if this is min max, right, you do the opposite of min max to get back the raw value, right? Opposite. Okay, let's say min max is something like this. Let's say x minus, use black color, x minus x min, x max minus x min, right? Example. This is your x array, right? This is from an x data set. So these are the minimum value, the maximum value. So what happens is you do the opposite. In order for you to find, this is a transform, right? So in order for you to de-transform, you just move this over, right, by multiplying the range. This is also called your range. So your transformed value, each of the transformed value, each of this, right? You multiply back this, and then you plus back this, so they will cancel away, you get the raw value, right? So the good news is you don't need to do this. If you use the sklearn, they have a inverse transform, right? You don't need to go to the mathematics, right? I mean, although this is not a lot of math here, but just moving around. But here, there's an inverse transform, which we cover in the video, right? You can actually use that to do an inverse transform. Okay. So in this example, right, when you untransform, let's say the transform value is 0.5. You untransform is, let's say, is 5, right? You can use this to explain, right? It's easier. You say that, oh, based on the business value, it is actually 5, right? For example, $5, or we are seeing the $5 difference between A and B, or before and after. This part, is it clear, or does it clarify on the business portion?
Oh yeah, Johnson. I want to untransform in Python. How am I supposed to do it?
Okay, so you can use the inverse transform because they have the same package, the scalar, right? The scalar, they have another package that I think is the property. Okay, you just call inverse transform. Throw in your transform value, right? Throw in, it's just like a function. You throw it in here. You throw in the transform value here by calling the inverse transform, and you can get back the original one. Remember the video that I shared the day for, right? There's a part where I show you the scalar. They have a few of the properties. If you don't want to use that, you can use the inverse transform package. Does it clarify? Correct. So the reason why we transform is just to meet the test requirement, maybe because they will pass the normality, right? So you might want to run normality again to check. But this will retain the same, as long as you retain the same shape, the results is the same. If you see that, what I'm trying to say here, the results, no matter if you use transform or not, because the shape is the same, the data is in the same distribution, so everything is the same result, except when you need to explain, you cannot use transform data to explain because people don't understand. Like if I tell you what is a log odds, right, you probably will scratch your head, what is log odds? But if I tell you the chances, right, of striking a lottery, right, okay, like percentage, so that is easier, right, than me talking about the transform version using log. That is one. The other one is nobody will understand what is log odds, or maybe min max. They may not understand what it is. The business may not know. Yeah. Okay. So this is another way, lah. Basically, this is another way. Okay. The third way is just the outlier. Because when you treat the outlier, you may get normality. Like this small part here, right? You may get normality, right? So if you see that actually, if you use one method, they may work. But if you use more than one method, right, they would work better. Because sometimes you transform, you still have to treat the outlier. If you know what I'm trying to say here. And if you really transform, right, you remove the outlier, then you have to know what you have removed before you explain to the business, right? Because you will say that, oh, I removed this outlier, but that is a transform outlier, right? So you also have to explain, right, that's based on that, I've removed this outlier, even the transform, all right? What is the value? Of course, you can inverse transform back to get the value that you have removed. Yeah. So again, these are just some ways you can work together. I mean, you can use this together, and it will often be able to help you get into your parametric. But again, if it doesn't, which it will not, right? It will not. So what happened, right, is you may want to check if they belong to other distribution. Okay, because they may not straight away belong to they may not straight away belong to parametric bell curve. Okay, there's actually other distribution under parametric as well. So this is the other distribution. Okay, then this one we call it alternative distribution. There are other alternative distribution. There is also free distribution, but these are all categories. So we just call it non-parametric, it's easier. So this other distribution like log normal. So again, I won't expect you to do all. We just check for at least two. Two is fine. Because if it's not bell curve, it's not Gaussian, then it could be log normal. And log normal is very easy to transform to this, right? I mean, you can use the transformation like min max or even log transform, right? You can transform that into Gaussian because they are like siblings. You saw in one of the slides which I show you. It's just an additional term log, right? And then the x. So you might have to check this because if they belong here, then you have to transform again, right? Same thing, you have to transform. It's just that you prove, the additional step is you prove that they belong to other distribution. All right, and then after that, the next step is to just transform back to normal, and then you test, right? You test for normality. Okay, and once it test successful, then you have passed this normality. This part here, this portion, the other distribution, that means it can be any other types of distribution that we may not know. It may fall here, it may fall under here. So if it fall under here, right, you straight away use non-parametric, right? Like let's say it belongs to a chi-square distribution, then you straight away use non-parametric, right? Because you don't need to test normality already, because they are not normal, right? Correct, but there are also other types of distribution data, like finance, right? Finance data set is not this. Usually, right? Usually it's this. Like it can be log normal exponential. It's like usually the values are tended towards here, or the factorial is here, right? Because it's very, very extreme, just like HDB data set. Or some data set is like this, right? So then you also have a uniform data set, right? Let's say you are testing a manufacturing plant, right? These are some other types of distribution that is under here, which you have to transform. Because if you don't transform, right, how can you carry out this? There's not much. There are a lot of different distribution. There are not much papers on the relevant parametric tests for them. There are papers on Gaussian, but there are not a lot of papers on this type, unfortunately. So therefore, if you have other distribution, right, then it's better for you to transform. And if the transformation fail, right, then you can say that this one doesn't meet normality, right? You can assume to use non-parametric. I mean, that's fine. After you try this out, then you say, cannot use this. Because there's no way for you all to know every single distribution, right? What are the so-called parametric tests? And some have not been developed yet, because this is a very fresh area, right? We can see that a lot of other distribution they may have some of their parametric tests, but they may also not have it, right? So the best way is just convert to this distribution normal. Yeah. Okay. Does it clarify? So the step, you see, we are going back to square one, is just to make this normality, because everything was designed because the parametric is much more, we said much more powerful than non-parametric, right? Statistically, because the results, when you get this correct results, you can actually explain well. But you get non-parametric result, doesn't mean that it's bad, but it is like it's less statistically powerful, which means that even if you explain, you may not have full confidence on the result, right? That's the truth, right? We use non-parametric, but that's it, right? I mean, this is just an alternative, better than not using any test, right? Then we use qualitatively mean to explain. Yeah. Yeah. Mm-hmm. Okay, you transform only the one you need to use, right? Because no point using the transforming others. And even if let's say you are just focusing on, let's say this is male, right? Then you only transform this one because you are not using the whole thing. Because like ANOVA, right, is looking at the intergroups. So you only provide what is required to them. We don't use the whole thing. Okay. Mm. Correct. Based on your hypothesis, lah. But if your hypothesis says it's everyone, right, then you have to do it for everyone, everything. Yeah, correct. Mm. 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 Correct. Mm. Yeah, using the raw data to explain it. Yeah, correct. Yeah, correct, correct. Yeah. Mm. No problem. Okay. How about the rest? Okay, clear, right. So, but for individual assignment, you don't need to do this much, right? Because individual, as mentioned, you just need to carry out one parametric test. If of course you want to do a little bit more, right? For mark, you can do that. But if you have already done the parametric test, you make some assumption. This is normal, right? I'm okay for individual. But for group, you have to do that steps. For group, you have to show that because it's part of working and form, right? So there's a little bit of work to do there as well as working constructively. Yeah. Yeah. Yeah, no worries. Yeah. Mm. Same data set. Yes, as mentioned, yes, yes, yeah. I mean, if you want to, it's okay lah, right? But you should not be copying lah, but you can work together lah. I mean, collaboratively work. But maybe some of you talking about this column and the other one talking about next column and all this. Yeah, it's fine. It's fine with me lah. Yeah. Okay. Then for group project, right? Actually, I added a link here. You can look at a past presentation of the intake one. So just to help you all, right, I just put it in here. If you want to know a bit more of in non-programming is also here, right? They have already completed their presentation. Yeah. Hmm. Yeah, because no, this one I don't have access. This one is not under me. Yeah, so you can look at it at your free time. It's open access until the school uh, removes it. Yeah, because depends on them, because I don't have this account. Yeah, yeah, it's not downloadable. Yeah. Mm. Mm. Okay, so I'll leave you continue. You can continue discussion, right? Or maybe by again same thing. Well, if afternoon around 12 plus, then we end. Yeah. So I'll go to other groups. All right. Thank you very much.
Thank you.
Thank you.